Okay, so I'm Andreas Rumpf, the original inventor and still lead developer of NIM. And so this is my talk, Move Semantics, which is the new stuff coming to NIM, inspired by Rust and C++, but we tweaked it. So let's get started. So the unofficial motto of NIM is actually copying bad design is not good design. And so that's already a useful motto because it tells us what not to do. So yeah, we should not copy bad designs. And more useful than knowing what not to do is knowing what to do. So paraphrasing this into recombine good bits from several sources. And so that's what we did. We looked at, as I said, Rust and C++ and Swift, how they do memory management, and if these concepts also apply to NIM. And it turns out the answer is yes. So here this is an example. So I have an array with 2 elements inside, and then I append the number 3 to it. And so this is a growable array. I think in C++ it's a vector, and in NIM it's called a sequence. So here is what happens in memory. We have this growable array, and it actually has a length and a capacity and a single pointer to a block of memory that can grow. And when we append a number, we need to, and since the capacity is already full, like we had capacity for 2 elements, we need to create a new block of memory, which is big enough to contain all 3 numbers. And we need to do something with the old memory block. And usually you would say, like, it's a realloc in C, and it would free the old block immediately. And now this is the most effective way of doing things. However, it causes a problem, and that is that? Yeah, okay. And the problem is that if I have other aliases to this pointer, I must ensure that it doesn't cause a dangling pointer. So here in line 2, I say I have this other variable, and it should have the same contents as some numbers. And if I do a shallow copy and just copy all the bits, then I would copy the pointer, which is invalidated in line 3 by the append, causing this to contain a dangling pointer. So that would be very, very unsafe, and it's a very bad idea. So to solve this problem, there are a couple of solutions. One is to deep copy the elements in the container, which is what C++ does, and also what NIM semantics do. You could also say, okay, so let's have a pointer to a pointer, so everybody gets the new update. This is done in Java and C#, I think. But it's slightly less efficient, because then you have another indirection. You could also say, well, this is an assignment, but it's a bad assignment, so let's just forbid it. Would be a terrible solution, but yeah, you could. The first solution, as I mentioned, you just have a garbage collector cleaning up this bad pointer for you, or only if no other variable refers to it. Or finally, we could move it, and that is the 5th point here. So we could steal the block of memory and perform a move, and that's also available in C++. So this would be an explicit move here in NIM, so you can do this. You can say, I'm going to move these numbers over to other, and then afterwards the source is invalidated, so it becomes an empty sequence. And so if you then append the 3, this is the only thing that's left inside there. So, and as you can see in line 6, after that, some numbers only has the 3 inside. So this is the explicit move. I mean, you can try to program in this style, and it's not really pleasant. So, but if it's explicit, it's okay. Like, you are aware that some numbers is empty afterwards. But there are plenty of cases where you can move implicitly. The first example, famous, if you have a result of a function call, you know it's not going to be used afterwards, so you can move directly into the variable a. Yeah, and then you could also say that uh, if you know that it's not used afterwards, this is what you can do. You can move it. So, and one design goal was to make this work. Like, okay, we know function calls can be moved, but I want to be able to name my results for readability without performance overhead. So, as long as named value is a local variable, the NIM compiler can see that named value is like it's used for the F call and that not afterwards anymore. So it would move the value, the named value into the F, and then it would move F's result into A. And here's another example. So I have a list with 3 integers inside. And if I say y is x, then since x isn't used anymore, we can move. And likewise for the set equals y. And so this works for local variables. So let's think about. Oh, I'm not gonna. Okay. Parameters do cause problems because we don't know if the value that's been pushed to our put is used afterwards. So this example is about like it's pseudocode for a hash table implementation. I mean, usually it would be more than 2 lines, but so we hash the value and we want to move this key value pair into the T. And given the current semantics, this would mean to make this expensive copy operation here. But you can annotate this parameter values to use the sync keyword. And then it's like the constraint that afterwards it shouldn't be used anymore, it bubbles up the call chain. So now, because it's a sync parameter, we know we can it won't be used afterwards, and we can perform the move inside the in line 3. So again, if I have values like a list with 3 strings inside, and I don't use them afterwards, I can move. Now, what happens if I use values afterwards? Then since we want to take ownership of the guts of this object, the compiler produces a warning for us, telling us like you are about to sync something that is used afterwards, and I will make a copy for you. So to ensure safety. So this has also been a design criterion. If you get it wrong, the performance suffers, but no weird crashes, please. So, and that's true. And the compiler warns about the performance aspect. And currently, this warning is overly, like it's a bit too aggressive. So I need to make this a bit better. So one solution here would be you move it around. Like if you echo the values before you embed it into this hash table, then it would work because the compiler knows echo doesn't want to take ownership of values, but table put does because of this sync annotation. So that's one solution. Of course, like if you are just adding some code for debugging purposes, you don't care if it causes more copies or not because this code will be removed soon again afterwards. Okay, so as I said, the sync parameter is an optimization. You don't have to use it. If you get it wrong, the performance is worse than before. If you get it right, you get better performance. And we are also working on inferring this property so that you don't have to annotate it at all. Because I went through the standard library trying to add these sync annotations everywhere, and I was like, yeah, no, I'm not going to do that. I let the compiler figure this out. So anyway, here are a couple of examples. So we have a hash table, and this is this putter or whatever, like insert or update. Then we have equality on some generic type T, or plus on T, and finally append or add on this growable sequence. And the question is where to put the sync annotation. And you don't have to guess, I'm telling you. So, oh, sorry, it's not really. Yeah, okay. So embedding stuff into a hash table takes the sync annotation, and the append for the sequences takes the sync annotation. And now so the first line is an insert or an update. And if I insert into the hash table, I also want to take ownership of the key. But if it's just an update on the table, I already have the key. And then what happens? Should this be a sync or not? Well, I don't know. But the thing is, if you do this with the sync, the compiler will actually ensure that this value is consumed for all cases, so you don't have to do that. And there is some notion of what it means to consume something, so we are going into destructors. Anyhow, so there's a different problem. Okay, so now I can put stuff into a hash table very effectively. That's good. How about how do I get values out of it? And again, the same problem. Like, and this is a result equals is the same as return statement in this case. But I wrote it as an assignment so that it's more obvious that this again is an expensive copy. So okay, we can now try to move this. And then the compiler will complain that T is actually not mutable. Like you cannot move out of it because move mutates the source. Okay, so and then let's make it mutable. Okay, this works. But now you need to think like what happens. Like you move the value out of this table, so you can access it exactly once, and then it's gone afterwards. So that's pretty bad. Unless maybe, I mean, if you have a pop operation for your stack, that's exactly what you want. But for a hash table, it's pretty shitty. So yeah, we need another annotation, which is lending a value, or lend v. And this is then a borrowing operation. So in Rust, this would be a borrowed pointer. In C++, it's a ref. So it's actually the same thing. And yeah, we need to ensure that once you borrow, that this doesn't outlive the collection's lifetime and stuff. But it's yeah.
It's like in Rust, but not like in C++ because they can't be checked.
Yeah. Okay. So the point is, in Rust it would be checked, and in C++ it wouldn't. And in NIM it is checked, except that we need to be better. So okay. So now that we understand how to optimize complex assignments, like deep copies or whatever you want to call it, we can apply this knowledge to something else, like take reference counting. Reference counting is basically the pointer assignment just simply got way more expensive than it used to be, because if I copy a pointer around, I need to increment the reference count of the source, I need to decrement the reference count of the destination, and then I can do the pointer copy. But if I'm able to move the pointer, then it could just be this bitwise copy, and maybe nullify the source afterwards if required. So this insight led us to the development of a new garbage collector mode. I mean, it's called GC, but GC is actually NIM's name for any kind of memory management that you want to. So, and here I have a benchmark. This is the binary, like this is a standard benchmark for throughput of a garbage collector. And so I don't expect you to understand all of this, but the point is now here, all the annotations like sinks and lens, they are not there. But even so, they work under the hood for us. And so we create binary trees and then trillions of these to some depth. And this is the main part. As I said, this is standard benchmark, and the results are really, really nice. So we have a couple of garbage collectors, so we can compare all of them. And the new one is fastest by quite a lot, like factor of 3 or 2 or whatever you want to compare it with. And memory consumption is about the same as before. For BermGC, I haven't been able to figure out the memory consumption precisely, so that's not available. So yeah. So now the question is, okay, this is very better than before, how does it compare to manual memory management? And NIM can do both, so you can use your own PTRs. So previously this was a ref in line 4, now it's a PTR. And to make a tree, we have this nasty allocation with a cast in line 12. And of course, we need to free the tree manually. So this is the recursive free. So first free the left, then the right, and then deallocate this node. And again, this. And now in the main part, we have to free these trees manually, which is very annoying. So in line 18, for instance, you can see this. Or in line 15, where you actually had to introduce a new temp variable just to be able to free it later on. So, and the result is it's still slower. I'm sorry, but here is the thing: what Arc actually does, it does optimized reference counting, and what the manual version does is basically I don't have a reference count because I know these are unique pointers. So if you add the machine word for this reference count back to this manual version, it's back to almost the same, to 6.2 seconds, whereas Arc is at 6.7 seconds. So there's still, and the memory consumption is identical under the assumption that I fixed this one bug that's left. So we are getting close to manual memory management, and for this particular benchmark, I think we can get to the difference into the noise level. But
the example was single-threaded, so are reference counts atomic, or?
No, they are not. We'll get to that. So, I'll get to that. Okay. There's a different benchmark for latency. I don't have the source code for this, but previously we had a soft real-time garbage collector, and the latency was 0.0.3 milliseconds for this benchmark. And now with Arc, it's better by over a factor of 3. The total runtime has been reduced also, and the peak memory consumption is also better. So not just throughput is better, but also latency. Now I've already outlined it. So what's going on under the hood is that we have destructors and move operators and assignments, and we can exploit them for other things, like they are exposed to you. We'll see in a minute. So you can now make your files close automatically after you. So that's very nice. And there's better composition between these custom containers. Like previously we had like manual memory management and GC memory management, and you must be careful not to mix them because it doesn't really work well. But with these extension points, the interop between these two worlds is much, much better than before. Okay, so here's another thing that we now can do. Again, the same benchmark, but now we want to have some object pool, or I think it's better called an arena. So we have an arena allocator, still dealing with these silly nodes which only have 2 pointers inside. So to allocate a new node, we basically check if there's a capacity left, kind of like for a sequence. And then but the node itself is an unchecked pointer, so we take the address of the element in the array, which is the backup storage for our node. And now here we can say, look, if you want to copy a pool, it's not supported because I couldn't be bothered to implement it. And so if you try to copy the full pool around accidentally, the compiler will complain and tell you like, no, you can't. And if the pool goes out of scope, the destructor is called. So this is in line 3. And of course, what do you do in a destructor? Well, you free the blocks of memory that's been and they have been chained in a linked list via this next pointer. And yeah, and then you need to change the program, unfortunately. So if you want to make a tree, you need to be aware of this pool where to get the new nodes from. And so this becomes a parameter of this make tree, and recursively you need to pass it on, as you can see in line 11 and 12. And now the bench. Okay. And now it's a bit easier to use because these pools are freed for us afterwards automatically. And in this case, I had to make two pools, like one for the long-lived data and one for the short-lived data. So that's, you can see this in line 5 and 14. And the question is, how does it perform? So that's the result. It's still much faster, over a factor of 2 performance improvement, and memory consumption is roughly the same. I mean, so yeah. Okay, so in summary, move semantics mostly work under the hood for us. They give us really good optimizations. 5 minutes left, okay. Yeah, we have seen the speedups, and they make the memory management deterministic. So what's actually the case here, so if you use a reference counting scheme and optimize it, what you can do is you can attach a cost model to your programming language. And once you do that, you get into the realm of hard real-time systems. So you can use NIM for hard real-time system with this technology. We have seen it improves throughput, latency, memory consumption, and threading. Well, I don't have an example, but as you can imagine, if you can move data from one thread to the other, and because you are guaranteed that this is kind of the last user of this data, then you cannot have data races. So it's a very nice feature of that. Yeah, it also improves the ease of programming. Like, just imagine your files close automatically and your sockets, and we get a better composition between these different container classes, let's say. Okay. Yeah, you can play with these benchmarks. I have uploaded them to GitHub. And yeah, if you don't know already, this is our website and the forum, and we are active on IRC as well. So that's my talk. Thank you for your attention.
So we have a live for questions. Also, the next speaker should come up and start preparing.
Okay. Questions? Yeah.
So is this available right now, or is this still a work in progress?
Well, it's on GitHub in the development. Oh, sorry, I need to repeat the question. So the question is how to get it. It's not in the version 1 of the language. Well, it will be our next major release this year. But you can already use it if you want to. If you use the development version of NIM. Yeah. Yes. The threading. No? Okay. Oh, sorry.
Okay. We'll come back.
Okay. Next question. Yes?
Could you talk a bit about the future plans for own?
For what?
Owned refs.
Owned refs. So yeah, we've been tinkering with owned refs, which is kind of unique pointers, NIM style. But I did these benchmarks, and I noticed that it doesn't pay off. Like so for instance, you can use this binary tree benchmark with owned annotations and use this new runtime, and I got the same number. So in this case, we didn't see the benefit. And so currently we do not know what to do with owned. Yes.
So my question was, how do you define visible after? And in particular, how subtle are you when there are if statements and stuff like that?
Okay. So the question is...
With a sub-question, which
okay.
is, are you familiar with the void safety in iPhone?
Void safety? But like from
so void in iPhone is equivalent
Eiffel, yes, void safety.
It's equivalent of nil.
Okay.
And they have these special cases for what they consider as void safe.
Okay, so two questions. The first was, how do we know that it's the last usage of a variable? The answer is we have a control flow graph and we track these precisely.
Sometimes it can depend on on, for instance, a conditional?
Well, it's in its conditional, then we know this. Like, say you move it in every case, then or how to put it?
Here's an example.
So
Let's say you move something in a loop,
yes,
and it's used. It's moved every time except the last one in the loop.
yeah, we noticed that. I mean, the compiler will tell you I cannot move because you use it in the next loop iteration. Oh.
So you're not trying
Exactly.
to be too smart about that.
We are smart enough about it, in fact. Okay.
You're,
Yes.
You're conservative in that case.
And the second question is void safety or nullability. It's also like work in progress. Like we want this not nil annotation in the language to guard us against this. And you're right. Like if you use an explicit move, you need a value to have afterwards to put inside the source, and then you need to make the pointer nullable just for that, right?
Yes.
But if you use an implicit move, we know it's not going to use afterwards, so we can simply pretend that nil is not a really value for your pointer.
So the reason I was pointing to void safety is
Yeah.
because in the case of iPhone, they decided to have things like if blah, then else, and they can say, for instance, if my test is specifically an
Yeah.
test, then in the then part it's considered to be void safe, in the else part it's not.
Okay.
You could do the same thing for moves. You could decide that if I have my move semantics inside an if, inside, if I'm in the condition for the test, then I can keep the move semantics, in the else I cannot.
Okay.
That's what I was referring to for being smart
Okay.
about the next one.
I need to think about it.
You do have time for another question if you want.
Oh, really?
So, yeah.
Okay, more questions. Yeah?
Because we have to wait.
Okay, it's not actually a question.
Okay, good.
I just want to say a big thank you because I learned that meme last year in Boston in a presentation, Lightning Talks. And I have to say to you big thank you because you saved me from the dilemma if I had to use Go and Rust, then like neither of those.
So you're welcome.